Welcome to lesson number 10. Learn C programming on the Raspberry Pi. Well, today we're going to be doing something a little different. We're going to be using the Raspberry Pi to control a very simple component, in this case a light emitting diode or LED. So let's begin. First we have to connect to our Pi. Okay, so we'll start by looking at last day's example here. And maybe take a minute or so just to review it. So last day we were still talking about functions. It was our last lesson on functions, where we talked about the whole idea of having a variable with global scope. In this case, amount is global to both main and to the function called total. So whenever we use amount in main, we are actually using the global version. Same thing in total. We're using amount here to compute it, and we're using amount here to print it out. Okay, so that's just a review on global scope and local scope, global variables or local variables. And what I'd like to do today is start talking about the Raspberry Pi and how we can write a C program to actually control some device. And the most simple example is an LED. So the first thing I'm going to do is I'll show you a circuit here that we've got. So this is the circuit that we are implementing. We have an LED. In this case, it's this clear plastic case LED. We also have a resistor in the circuit, which is right here. And for our switch and battery, we're basically using the Raspberry Pi. So if you look at this black lead here goes to ground on the Pi, and the red lead goes to I believe it's goes to a GPIO pin 25. Okay, well, we'll explain all that. I know it looks kind of strange to people who have no electronics background, so we'll go over this really slowly. Let me bring up another diagram. May clarify the situation a bit. It's this one here. And what I'll do is I'll explode it here, make it bigger so we can see it. So this is basically the circuit that I have implemented on my desktop. So if you look, I have an LED right here, this one, and the LED is connected on this breadboard. By the way, you can see this little crooked leg here. This is the anode. Okay. And the cathode is the shorter leg. So so the anode is going to be connected directly to, if you look here, it's GPIO pin number 25. GPIO stands for General Purpose Input Output. So we are connecting it to GPIO pin number 25, or GPIO 25. The other side of the LED goes to the resistor. This happens to be a 100 ohm resistor, and when it comes through the resistor, it ends up going to the ground pin, GND. Now if you look at the pins on the Pi, they're labeled, the actual physical numbers of the Pi. This top right hand corner here is pin number 1, and then we have pin number 2 is bottom right corner, and then 3, 4, 5, 6, 7, 8, 9, 10, all the way to 25 and 26. Remember, this is the original Pi, so it only has 26 pins. So the actual physical numbers are 1 to 26. But we're going to be using what are called the GPIO numbers. And you see this little diagram here, it shows us what the numbers are. So we're going to be using this one, which is GPIO number 25. Okay, so this is the diagram we're using. So the whole idea is that if we can get a program to put 3.3 volts onto pin 25, GPIO 25, that 3.3 volts will go through the LED, through the resistor, and back to ground, and it will thereby turning on the LED. If we put 0 volts onto GPIO 25, then that will turn the LED off. Okay, so that's basically all we're going to be doing. So let's see if we can get a C program to do that. And by the way, the reason we put a resistor in the circuit here is to avoid shorting out the GPIO voltage here. Like we have 3.3 volts are on GPIO 25. If we had no resistor, then that voltage would just go to ground, and it could do some damage to our Raspberry Pi. So that the purpose of that 100 ohm resistor is just to limit the current going through the LED. If you're not familiar with resistors, you can always go to the web like this. Let's just do a Google search for resistor color codes, and you can see they have calculators online where you can select, for example, the resistor we have has 4 bands on it. I believe it's first one is brown. I think the next one is also, no, let's see, 1, 0. So it should be a black and then a brown, and that gives us 100 ohms. And the fourth one could be a gold or something. This tells you the tolerance of the resistor, so 5%. So it's 100 ohms within 5%. So that's the resistor we're using. So you don't have to memorize any of the color codes on the resistors. You know, these colors here, you can just bring up a website, type in the colors you have, and it will tell you the value of the resistor. Okay. So let's go and write some code now. Close these guys up, close these guys up, and I'll close this, and I'll start a new file. Okay. Now, we usually start by including stdio.h because we want to use printf and scanf. But in our case, we're not going to be using printf and scanf, which are standard C library functions. We're going to be using functions provided by the wiring pi library. So I will include the header file for the wiring pi library. You notice it's the uppercase P here. Okay. Now this library, the wiring pi library, comes standard with the Raspbian system. So if you're using some other Linux on your Pi, you might have to install the wiring pi library yourself. But for Raspbian, it's already there. Okay, so what we'll do now is we'll just start with our main. Let's see if we can get something going here. Now, the first thing we have to do is we have to initialize the wiring pi library software. So we have to call a wiring pi function. So I'm going to call this function called wiring pi setup GPIO. You notice there are uppercase pi, uppercase S, uppercase G. So this function is part of the wiring pi library, and it's used to basically configure or set up the library for our use. Okay. Once I do that, I want to tell it. I want to tell the library that I want to use pin number 25 as output. So and I'm going to say I want pin number or GPIO number 25 is going to be used as output. So let me just say 25 is equal to the GPIO number, and 1 means output. Okay. And then, of course, what I want to do after that is I want to turn the light on. So if I turn the light on, I have to use another wiring pi function called digital write, and I want to write to GPIO 25, and I want to write 1. A 1 means a high, or 3.3 volts. So I'm going to put 3.3 volts on that LED. And then what I want to do is I want to wait for a bit, so I'll call delay, let's say 2000. So this is wait for 2000 milliseconds, or 2 seconds. And then we have to turn the light off. So this way I'm going to, by the way, this 1 over here, 1 is equal to high voltage. 0 to 3.3 volts. So what we're going to do now on this line here is I'm going to turn that voltage off. 0 is equal to low voltage, which is equal to 0 volts. And we then return 0. That's it. So let's save this guy here. We'll save him as, and I'll put it into lesson 10. And I'll just call it led.c. So there you have it. So let's go over this again. The first thing we have to do is we have to include the header file for the wiring.py library, which is called wiring.py.h. Then in our main program, we initialize the wiring.py software. So wiring.py setup GPIO. So that this tells that I'm not using physical pin numbers, I'm using GPIO pin numbers. Then I say another function belonging to the wiring.py library is pin mode. I say I want GPIO pin 25 to serve as an output pin. So what that means is I'm not going to be reading what information is on that pin. I'm going to send information to that pin. I'm going to send either a 1 or a 0 to that pin. And then we have the function digital write. We write a high voltage, turns the LED on, and then we pause for 2 seconds, and then we turn the LED off, and our program is done. So in order to compile this guy now, we're going to have to include the wiring.py library. So -L wiring.py. So you'll notice in previous lessons I showed you how to include libraries. For example, we included the math library by saying -LM, or we include the C library by saying -LC. In this case, we want to include all of the functions belonging to the wiring.py library, so we say -L wiring.py. Don't forget, you need a capital or uppercase P here. Okay. Well, let's see if it compiles. Oh, I have to be in the right directory, sorry. Lesson-10, and I'll just recall that command. Oh. What's wrong with this? Oh, digital. I spelled digital wrong. D-I-G-I-T-A-L, and I got S-L, so A-L. And let's save that again. I told you when I do things off the top of my head, I make mistakes. So bear with me. We made the correction. We saved it. We'll try to recompile. Okay. So we recompiled, and now we can run our program. We should have our executable code here called LED. So I can just say /LED, and you see the light goes on and then it goes off. So it's on for 2 seconds. 1001, 1002. Try it again. Well, it does work. Okay, well, let's do something a little more interesting here than just having it do that. What we'll do is we'll put this into a for loop and make it blink a whole bunch of times. We'll put a local integer in main called I, and then I'll make a for loop here, and in the for loop I'll turn the guy on, and I will delay here for 1 second in this case. And then I will turn it off. And then I will delay again for 1 second. And that ends my for loop. So let's go over this code slowly, see what we're doing. Again, we start off in main. We create a local variable called I, because we want to use that as a counter in our for loop. And we initialize wiring pi, and we set GPIO to output, and then we do this loop 10 times. So these 4 lines are going to be repeated 10 times. So the light should come on for 1 second, then it will go off for 1 second. Then it will go on for 1 second, then go off for 1 second. So let's see how this works. I saved it. We'll compile it again. And now we can run it. And we'll see how it works. So the light goes on, off, on, off, on, off. And it does this 10 times. So this is really the beauty of the Raspberry Pi, in that we can actually write programs to control devices. And of course, the simplest device I know of is just a simple light emitting diode. Okay, well, let's go back to our code here and see if we can fix it up to make it a little bit neater by using more of the definitions that are given in the header file for the wiring pi library. So for example, the first thing is, instead of saying a 1 here, we can use the uppercase output, because this data here, output, is defined in wiring pi.h as a 1. Okay, then here, the 1 in the digital write, we can set that to the keyword high, because that makes it into 3.3 volts. And again, that high is defined in wiring pi.h. Okay. And of course here we can say low. So this makes a little more sense now, instead of using a 1 and 0, which a lot of times people get confused, you know, which is output, which is input, which is high, which is low. So we can use these predefined values. So I'll try compiling it again, and it compiles successfully, and I can run it again, and it will work just as it did before, because those these values, output, high, and low, are predefined for us in this header file. In fact, I think we might be able to see it in more slash usr slash include wiring pi.h. So if we look at this, the header file, which is located in the directory user include, if we look at that header file, we should be able to see these these data values here being defined, output high and low. So let's take a look, see if we can find them in there somewhere. So there you go. If you look at output, it's defined in the header file as a 1. So that's why in here I could have put a 1, but it makes a lot more sense to use the keyword output. And low, or not high, sorry, not high, I'm talking about here, I made a mistake. For output, I could have used a 1, or I could use the keyword output, because output is defined as a 1. Now what about high and low? Well, they're in there somewhere too. There they are. A low is defined as a 0, and a high is defined as a 1. So that's why I could have put here, in fact I did put a 1 here and I put a 0 here. But since these definitions are included in the wiringpi.h library, then we don't have to use 1 and 0. We can actually use these words that make a lot more sense. Okay? And speaking about these number sign defines, I can put one in my own program for the GPIO number. I could put in here, for example, number sign define. I could call it LED underscore GPIO, and it will be 25. So now, instead of using 25 here, I can put LED underscore GPIO, and here as well LED underscore GPIO, and also here LED underscore GPIO. So now I've included my own definition here for LED GPIO is basically GPIO number 25. So I can compile this, save it, quit. I'll just recompile, and I can run it again. And again, I have 10 times on, 10 times off. So whenever you use the word, this keyword define in C, number sign define, it's basically just a replacement. So wherever the compiler sees LED GPIO, it's just replacing that with the number 25. Wherever it sees output, it's replacing it with a 1. Wherever it sees high, it's replacing it with a 1. Wherever it sees low, it's replacing it with a 0. Okay? So it just makes the program a lot easier to read and to understand. Okay, I have here some other LEDs. I can show you them here in my hand. Some of them are red ones, some of them are blue ones. You can't tell until you actually turn them on, but they usually cost like 25 cents each or something, so they're fairly cheap. Okay, so you can buy a dozen of them, different colors. Okay, again, if you look at the length of the lead, see, one lead is long, that's the anode, and the other lead is short, is the cathode. The other thing you'll need is a breadboard, and these breadboards might cost a couple of dollars. And there are different sizes. There are large breadboards or small breadboards. And then of course you'll need some hookup wires. These wires have, they plug in, with male and female connectors. So probably you're looking at a couple of dollars for the board, $1 or so for some LEDs, another $1 for some resistors, another $1 for hookup wires. So you're looking maybe, $5-10 worth of parts to actually build something like this and to start working on it. Okay. So that's probably all we need for today. If you don't know where to buy these components, then if you're living in Toronto, your best bet would be to go to, for example, where is Creatron? Creatron is a store. They have 2 locations. If you look, they have the Scarborough location and the downtown location. And you can buy all the things you need at this particular store. Okay. There's another place here in Toronto that you can go to besides Creatron. You can go to Canada Robotics, and they are located, where are they? Right here, 800 Denison Street in Markham. So that's just outside of Toronto, if you live in the northeast corner. You can buy all of the components you need there. Okay. So, my advice, get $10. Go to these places, buy some of these components, buy some wire, buy some LEDs, buy some resistors, buy a breadboard, and start building stuff. And as we go on, we will start using more complicated components in our course here, in different lessons later on. Okay, that's enough for lesson number 10. Let me sign off and stay tuned for lesson number 11.